Hey, this is Dr. B, and let's talk about bonding. A chemical bond is the force that holds two atoms or ions together. It's that line, if you will. A good question to ask is which elements don't form chemical bonds, and those would be, except under extremely stringent conditions, the noble gases. And that's a clue. Why do elements form bonds? Well, perhaps they want to become like the noble gas. They want to obtain those noble gas configurations, which for everything except helium is a full outer shell of 8 electrons. And they can do that by either sharing electrons, transferring electrons, or just having a mobile sea of electrons. In the latter case, the noble gas configuration is not obtained, but some stability is. So, if the bond is between metals, well, they're not going to have that noble gas configuration. They all are going to technically have two valence electrons. Complicating matters will be an unfilled inner shell in most cases. Those electrons are found to be very migratory in nature, so much that they call this a mobile sea of electrons. And here we're dealing with everything that's left of the staircase. Those are the metals. This is a metallic bond. An example would be the iron-to-iron bond. Since it's an entire lattice, it's not an individual diatomic substance like this. It extends in all directions, three-dimensionally. If it's between a metal and a nonmetal, that would be left of the staircase and right of the staircase, metal to nonmetal. Then you have an ionic bond, and in this case it involves a transfer of electrons, not necessarily directly, but these have lost electrons, these have gained electrons, and by doing so they can both assume noble gas configurations. They'll be oppositely charged, they'll be attracted. It's wonderful. Sodium chloride is an example. Sodium lost one, chloride gained one, rendering them both with full outer shells. Now, perhaps the most interesting one, because these are simply, binary typically in nature, these are usually just the same element unless they're alloyed, in which case it's a physical change anyhow. But nonmetals, now you can get very creative. These are the small area to the right of the staircase. And in this case, you can have sharing of electrons. And we'll show this in detail. And this can lead to covalent structures. The carbon to chlorine bond involves a sharing of electrons, such that by sharing they can obtain noble gas, sometimes called pseudo-noble gas configurations. And the really cool thing about this is that they can extend. This carbon can also have a covalent bond with something else over here, leading to an infinite number of possibilities. You can also have something that's not discussed as much. That's a covalent network solid. That's kind of analogous to the metal lattice that you have, but involving nonmetals. Things like diamond, graphite, glass, and others form these very strong network solids. Within the realm of covalent bonds, they can be shared evenly or unevenly. We call it nonpolar if it's an even sharing of electrons, and polar if it's uneven. The carbon-carbon bond, since they both have equal desire for electrons, being identical elements, would form a nonpolar covalent bond. No partial positive or negative charges as far as you can see based on that bond. However, oxygen is far more electronegative. It is pulling electrons away from carbon towards oxygen. Not so much that it's a ionic bond, but it's a polarized bond. A little plus for carbon, a little negative for oxygen. That's a polar covalent bond. An exception, since after all, hydrocarbons are so greasy and nonpolar is the carbon to hydrogen bond, that is considered a nonpolar covalent bond. Okay, let's test it. Is it ionic, covalent, or metallic? Sodium chloride, ionic. Fluorine, two identical nonmetals, I'd say covalent. You could even say nonpolar covalent. Iodine, same deal. The chlorine to magnesium, and I think that too should not be there. That chlorine to magnesium bond is a metal to a nonmetal. I'd call that ionic. Carbon dioxide is two different nonmetals, therefore it is a covalent bond. Is it a polar covalent bond? I think the individual bond is, but the molecule is not. The sodium to oxygen bond, metal to nonmetal, that's ionic. Iron bonded to lots of other irons, that would be metallic. So the rule is if there's a metal present, it's going to be either ionic or metallic, and if it's just alone, it's going to be metallic. That is an introduction to chemical bonds.